So I'm going to cover two things today. One is multi-level modeling for ego networks, and the other is ego network dynamics by request. I might go over, so just by vote, how many of you are more interested in ego network dynamics? This is about like the order. How many of you are more interested in multi-level modeling? Okay, well this is not helpful. It's about equal. Okay, maybe a little more for multi-level modeling. Okay, all right, okay. Okay, so then we'll start with multi-level modeling. So I find that a lot of people are really intimidated by multi-level modeling. They don't really understand it. So what I'm gonna do today is try to break it down for you in a way that makes it super simple. We're not gonna do any like lab work or modeling. I will show you what output looks like. But mainly I just want you to understand it conceptually so that you're not intimidated to sort of dig into whatever software program you like to try it out. So the basic idea behind this is that we can think about alters as being nested in egos or in ego networks, right? And so this is sort of your classic hierarchical or nested situation. And typically when we're studying ego networks, we have lots of these clusters or lots of these networks where you have alters nested in egos. And we can think about that as being super analogous to something like students nested in schools or observations over time being nested in people. So we can model it with MLM, and that has a lot of advantages over either aggregating to the ego network level where we just lose a bunch of information, or other things like just treating the variance in the clusters as a nuisance, right? We can actually explicitly model it and learn some things about how our data are structured. So I'll just start with the boring stuff, which is when you can use MLM for ego network analysis. So there are some formal requirements. The most important one is that your dependent variable is an alter or a tie level variable. So if we think about level 1 being the alters, level 2, like think about an apartment building, is your egos. Your dependent variable has to be at the alter level. So it needs to be a characteristic of the alter or a characteristic of the dyad that varies across egos. So if you're interested in predicting a characteristic of the ego, which we often are, something like health or employment outcomes or social movement participation, then MLM is not appropriate, right? So here you're going to be predicting something about the alter or tie. So the independent variables can be at any level, which is great. It's super flexible in that way. So you can model characteristics of alters or of dyads based on things at the ego level, so ego gender, education, health, things at the network level, so you could use network size to predict what alters are doing, for example, or at the alter level. So maybe alter gender or alter level of support predicts some other alter characteristic. So that's the most important one. The other two are a little fuzzier. Don't tell anybody I said that. The second one is that the personal networks of egos don't overlap. So if you're in a situation where you have like a village or something, and so there's like a ton of overlap between alters and networks, then you're looking at a cross-classified situation. You can still do MLM, but it's a more complicated model. Sometimes it's hard to get it to converge. I'm not going to talk about that today because it's more advanced. So you can still do it, but it will just look a little different than what I'm doing here. And Rafael Vaca has some really nice resources on cross-classified models for ego networks. So look into that if you're in this kind of a situation. If the overlap is negligible, right, like a few alters here and there, then it's fine. You're pretty safe to ignore that level of overlap. And then the third one is that the ego observations need to be independent of one another. So this is kind of like the OLS requirement that all your observations need to be independent. That's why we need MLM to start with, right? If you have like students in schools. Here, the same thing is true at level 2. So your egos need to be independent. Again, it's a little fuzzy, right? If you have some people, some egos that might be related a little bit, then it's probably okay to ignore it. Okay, so in terms of the kind of research questions that you can address with multi-level modeling, so we could ask, for example, what kinds of things affect the types of ties that an ego forms, right? So what kinds of egos form ties to particular kinds of alters? So like who forms cross-racial ties, for example, or like racially homophilous ties? You can also ask about what affects alter behavior or alter contributions to ego. So you could say, what kinds of ego characteristics or network characteristics might affect whether alters provide different kinds of support, for example, or caregiving, or whatever it is that you care about. And then you can also ask what affects characteristics of dyads or relationships. So what ego and alter characteristics might affect things like the likelihood of sexual activity or the amount of conflict or whatever between members of a dyad. And so it's really flexible. You can do a lot of really cool things. And the alternative, really, which people often use if they don't use MLM, is to just aggregate everything to the network level, which creates kind of an ecological fallacy situation, right? So, so in other words, I'm just aggregating. So maybe I want to know whether an ego is likely to have cross-gender ties. If I'm just aggregating to the network level, then I'm asking what kinds of egos have what proportion of women in their network, for example, right? And so then I can't really look at the characteristics of those individual alters that might be affecting that relationship. Okay, so hopefully I've convinced you that this is a worthwhile thing to do. What is multi-level modeling? It has like a million names, which when I started to use MLM, I was basically self-taught, and one of the most confusing things was the fact that there's like 800 names for what is essentially the same thing. So all these different words on the screen are basically just different kinds of nested models that are really quite similar in a lot of ways. So hierarchical linear modeling, growth curve modeling, or growth modeling if you're doing longitudinal analysis, fixed effects, random effects, variance components models, blah, 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 right? These are all basically just different flavors of multi-level models. So don't be afraid of these. You can just ignore them. And so the key thing about multi-level models is that there are two major parts of any model, any like standard regression model, right? You have two parts of that model. One part of the model is the model that we tend to care about most and pay attention to, and I would just call that the model for the means. So these are what we call fixed effects or fixed parameters, and these are like your beta coefficients. And so these are the things that we're used to caring about when we want to predict something. Right, so this is the effect of X on Y. So how the expected outcome for a given observation varies on average as a function of some predictor variables, right? So that's the fixed part because we have these fixed parameters. There's another part of the model that we usually just ignore. Or if you're a good scientist, you'll test some assumptions about it, but we don't really care much about it beyond that. And that's the model for the variances. So these are called random effects or residuals, errors, and we can call these stochastic or varying parameters. These are all sort of words for the same thing. And it's just the part of the model that's the variance that we just tend to care less about. And we often just make a lot of assumptions about it. And if we're doing a good job, we'll test those assumptions. But other than that, we don't really care about them. And this is really the difference between MLM and a standard regression model. It's how those residuals, right, or how those varying parts of the model are distributed and related across the observations. So that can be people or groups or time. That's the main way that this model differs from a general linear model. And we mostly are going to ignore it and not care about it. So not intimidating, right? You guys can totally do this. So the reason why we need a multi-level model is because it violates OLS assumptions, right? So what we really want to do here is model what's called dependency or autocorrelation across observations. So for example, if you have people, children nested in families, kids nested in schools, observations over time nested in individuals, those observations at the level 1 ground floor of the apartment building are going to be more similar if they're nested in a common cluster than they are to any other observation. And so that's a violation of OLS. So where does this dependency come from? So there's two sources, and this is going to be related to the two major kinds of models that we're going to do in multi-level modeling, a random intercept and a random effects or a random coefficient model. So the first source of dependency is in mean differences across sampling units. So if we're talking about social networks here, our sampling units are egos, right? But they could be schools, families, etc. So we have these mean differences across these units, and that's a source of dependency. And so we're going to use a random intercept in our models to represent that source of dependency. The second source of dependency is about differences in the effects of predictors across sampling units, right? So in a longitudinal model, this is individual differences in the rate at which people grow and change, for example. In a clustered model, it's group differences in the slopes of predictors. And this is represented by random coefficients or random slopes or random effects in our models. And so just to provide an example, my ego network, for example, might be more supportive on average than your ego network, right? Or less supportive. And so we have these differences where my alters are more similar to each other than they are to your alters. That's the example one. Example two is that the effects of some predictor in my network might be different. The slope might be different than the effects in your network. So, maybe for me, gender is more important in terms of predicting supportiveness in my network than it is in your network. Okay, so why can't we just ignore it? So if we ignore this dependency and just model it as an OLS, as though all the observations at level 1 are independent, then it has implications for statistical validity, right? So it depresses our standard errors and it makes things look significant when they're actually not. And then it can affect parameter estimates, or it can affect the fixed part of your model, or the betas, if it's extreme, if dependency is extreme. So you're essentially sort of making the wrong conclusions, getting the wrong answer. And so what an MLM does is it just accounts for clustering, or it accounts for this non-independence, and allows you to explicitly model it in the way that the regression model is structured, rather than just controlling for it. Okay, I'm going to stop here and ask if there are any questions. I'm going to walk through the most ridiculous example that, if you're a little fuzzy, will hopefully make things clear. But I'm happy to answer questions now. Yes?
To what extent, if any, does this care about alter-alter ties?
Yeah, right. So alter-alter ties are going to always be aggregated to the network level, right? Because it can't model that level of dependency, right? It can't model whether an alter has a tie to another alter. What it can do is, it can model alter centrality, for example, right? So as long as it's a characteristic of that alter, it can model that. It can't model the full network structure of relationships between alters. Does that make sense? That's a great question. Other questions? You guys are just totally on board. You're like, I've got this. Great. Okay. All right. Then I'll continue. Okay. Oh, this is so fun. Do you guys love formulas? I actually hate formulas, but it's good for sort of forcing you to understand. But I'll walk you through it slowly, because this stuff doesn't come super naturally to me either. I have to really learn and visualize it in order to be able to understand and teach it to other people. So this is what your general linear model looks like, right? So you have your y sub I, which is your dependent variable. So the I with the little subscript means is that basically each observation in your data set gets their own, right? That's what that means. If it doesn't have a subscript, it means it's a fixed parameter, right? Or sorry, if it doesn't have a letter subscript. Beta sub 0 is your intercept. Beta sub 1 is a coefficient. X sub I is the value of x for each observation of the data set. And E sub I is your error term. So this is the thing that we're used to just ignoring and making assumptions about. But each individual observation in your data set gets its own error, right? Which means that it's stochastic, or it's a varying parameter, or a random parameter. Okay, so what we do in regression is to try to minimize the error by adding covariates that explain as much variance as possible. That's literally all what we're doing with a regression model, right? So we want to understand how variables are predicting other variables, and we want to predict as much of that with the stuff that we know as we can, so that what's left in the error is as small as possible. So this is essentially what OLS does, right? So with ordinary least squares regression, we want to draw a regression line that just minimizes these error terms. But you can see that these are all the observations in my data set, and each observation gets its own error, or its own variance from the mean effect, right? So each red arrow is error, because the line of fitted values doesn't go through every data point, right? So there's always going to be error. So how we treat that error is the only thing that's different about multi-level modeling, right? Okay. So the problem with multi-level modeling, or the problem that leads to the need for multi-level modeling when you have clustering, is that those error terms for observations that are clustered within, for example, an ego, are probably going to be correlated, right? Because my alters are going to be more similar to each other than they are to your alters. And so this violates OLS assumptions. So what we're going to do for the random intercept model, which is sort of the most basic form of a multi-level model, is we're just going to split that error term up. That's all we're going to do. So we're going to split the error term, that red arrow that we had before, into two different parameters. One is called zeta. That becomes our random intercept. And then we have an error term. So essentially what this means is that each cluster or ego network is going to get their own zeta, their own random parameter. And then the error becomes the extent to which the alters differ from that zeta, right? Rather than from the overall regression line. So we explicitly model this error dependence. We just split it up into these level 1 and level 2 components. So we're going to have this random intercept for the level 2 person, the ego, and then that's going to be constant across all my alters. And then again, I have an error term for each observation or alter clustered around my zeta, right? Or my random intercept. I'm going to show you pictures. I'm very visual. So we can think about this very simply as we have this pile of variance, right? This pile of unexplained stuff, and we're just going to split that up into two types. So one is going to be between cluster variation, so level 2 sort of inter-cluster differences. And then that tells us essentially how and why does one ego network differ from another ego network. So if my intercept is high, it means that my network is higher on whatever thing I'm predicting, right? If it's low, it means that my network is lower on average than on whatever we're predicting. And then we have within cluster variation, or our intra-cluster differences. That's our E or our epsilon, which tells us how and why do alters within my ego network differ from other alters in my ego network on average. Okay, here's just a visualization of the same thing. In OLS, we have our error term, our residual variance. We're treating that all as error. Now we're splitting this up and we're saying it's not just random error, right? There's something non-random about this because my alters are more similar to each other than your alters. And so some of that's going to be error, but some of it is going to be this random intercept, which tells me something about how my network is different from yours. So we're just making piles of variance. We aren't reducing variance. We're just splitting it up differently into different terms. And so it's going to look essentially like this, right? So now you have a Y that is specific to each alter within each network. So that's what the IJ subscript looks like. Familiar, familiar. Again, our X is now specific to I and J. We have our random intercept zeta, and we have our error term. We can look at the total variance then and think about it as a function of variance within clusters as a function of total variance, right? So again, we're just splitting up that variance. These two terms, the theta and the psi, so variance within and between clusters, are the main components of a term, if you've used multi-level modeling, you've probably heard before, intra-class correlation, which is, or rho, which is just a measure of between cluster heterogeneity or within cluster homogeneity. They're two sides of the exact same coin. So essentially that tells us how correlated alters within a network are. So the higher that is, the more correlation there is between alters in the same network, the more we need multi-level modeling because it suggests there's more dependency, right? And so we just call this the interclass correlation, or ICC, and we always model it, right? We want to know how similar are alters within the same network, or how similar are my observations over time relative to other people's observations. And so this is just another way to look at it. This is kind of a shitty drawing, sorry. I didn't draw this, you guys, it came from a book. But you can see at left here, right, we have a bunch of clusters here at the bottom. And then you can see that the observations, these are the zetas, right, or the random intercepts. And you can see that over here, the ICC is smaller because the observations are less clustered around the intercept. Over here, they're more tightly clustered, right? So we have a higher ICC, or higher correlation of observations within our clusters, in our case, our ego networks. So this is just a standard way of expressing how much do we need to worry about dependency due to cluster mean differences, right? So if we have a bigger ICC, we're going to have more messed up standard errors if we just use OLS and we ignore clustering. Okay, so this is the ridiculous example. I changed it once to something more appropriate. And then somebody that had been in my workshop was like, you should not do that because now it's more boring and people don't pay attention. So then I changed it back. So we're going to roll with it. Okay, so let's suppose that I have a bunch of dyads, a bunch of couples, right? And I want to predict how often are those couples having sex, right? This is something that's important in our daily lives, theoretically. And so I have my formula here. And so I'm essentially predicting something that's happening at the level of the dyad, right? Or at the level of the relationship. And you can imagine that if you were someone that had multiple sex partners, you might have different sexual frequency with different partners, right? And you might also imagine that those would be clustered within egos, right? So some people may be more sexual than other people, or they may have time constraints, like children, that keep them from being more or less sexually active with their partners or whatever, right? So here's where we might see both within and between network differences in this dependent variable. And so one thing, for example, that might predict this is how many instruments the altar plays. We all know that playing instruments is very sexy. Some of you may have attended band camp or be a fan of rock and roll bands, groupies. We've all seen, what's that one movie? Almost Famous, thank you, right? And so we might want to predict frequency of sexual activity as a function of how many instruments the altar plays, right? Okay, so here's an example of what this would look like in a multi-level model. So suppose we have two egos, Jane and Joe, and between them they have 5 sex partners, right? Or 5 altars. So these are their altars, right? So this is Jane's zeta, or Jane's random intercept. This is the overall intercept, or the mean intercept for the sample as a whole. This is Joe's zeta, or Joe's intercept, right? And so these are Jane's sex partners and Joe's sex partners. So based on this illustration, what can we say about Jane and Joe's sex lives? Say that, sorry. What'd you say?
I said who plays instruments.
Well, right, yeah. So Don 1 probably plays many instruments, if our theory is correct. What were you going to say?
I was going to say Jane is having more sex than Joe, but the
Yes.
variance for Jane is variance.
Yes, exactly. Yes, exactly. Perfect. So because Jane's zeta is positive and it's above the overall sample mean, right, we know that Jane is having more sex than Joe. And yes, there's more variance within her altars. So her within network variation is greater. But we can also look at sort of variation within and between. And we can see here that variation between overall is quite large, right? So there happens to be more variation between, in this example, than there is variation within. Okay, perfect. Great, you got it. So that's it, right? So that's all we're doing is splitting up the variance, right? Because we know that egos and ego networks might be systematically different from one another, rather than just treating all these observations as though they're independent, because they're not independent, right? And so what we do next is that both Jane and Joe are going to get their own random intercept. And so we're just here changing the intercepts, right? We're only adding an intercept. We're not adding a slope yet, an individualized slope, but we will. And so this is the overall intercept, and we can see that Jane's intercept is higher and Joe's intercept is lower, but all in all, the slopes stay the same, right? So in a random intercept model, the slopes are going to be parallel. And so as we predicted, the more instruments an altar plays, the more sex that couple is having. And so we'll just then repeat this for every person in our data set, for every ego network in our data set. So every ego gets their own regression line. The intercept is random, which just means that it varies. I kind of hate that term because it's not actually random, right? But that just means we allow it to vary in our model. The slope is constant. And so the overall intercept that's reported in this data output is not the same as if you just independently took an average of all of the observations. It's a weighted average. It's a weighted average of each ego's intercept. And so it's not the same intercept that you would get if you used level 1. It's weighted by the variance within networks and by how many altars are in each network. So in other words, networks that have more altars and less variance provide more weight to the overall intercept that you're going to get. Does that make sense? Okay. Okay, so what if the effects of X on Y within ego are different, right? This is possible, right? So it could be that Jane is super motivated to have, yes. Oh, yes, sorry, yes.
Question is thinking about for certain egos, maybe their alters are more similar because there's more ties among the alters. And if that's the case, it's a little different from just like ego difference. Can you tell me how do you differentiate those two conceptually?
Yeah, so that's a great suggestion, right? So maybe all these sex partners know each other, and that could affect how much sex they're having, right? You would just model that as a network level property. So you could measure, for example, the density or the weighted strength of ties between alters, number of alters who know each other, right? There are a lot of ways to model that, but you're going to model that as a feature of the network. You could model it as a feature of the alter. So you could say, how many alters in the network does this alter know? And then it becomes a property of the alter. But you're just going to model it as an independent variable. And it should eat up that variance that you're talking about. And then you can explicitly model it, right? Which is kind of an interesting question. Does that make sense? Okay, great. Okay. So what if the slope is different, right? So maybe for Jane, how many instruments their alters play is super motivating and super important in terms of how much sex they're having with their alters. But for Joe, it matters less, right? So we might want to explicitly model this kind of clustering or dependence as well. So we're going to do that with the random coefficient. And so again, we're just splitting up piles of variance here. So now we're going to have two zetas, right? One is going to be an intercept difference for each ego network, and the other is going to be a slope difference for each ego. And so it just looks like this. So we have sort of our overall weighted average regression line, right? And then we're going to have, this is just parallel to this line. So Jane is going to have her own zeta, which is the extent to which her slope differs from the overall slope. And she's going to have her own intercept, which is the extent to which her intercept differs from the overall intercept. And Joe's going to get the same. So again, we're just splitting up the variance into things that are more meaningful because they're actually non-random. So in this random intercept or random coefficient model or random effects model, every ego gets their own regression line, but now they're not parallel, right? So the intercept is random, which means the intercept varies, and the slope is random, so the slope varies. And again, the overall intercept that Stata or R or whatever spits out, and the slope that it spits out are weighted averages of egos, intercepts, and slopes, not of the overall observations. So they're going to be slightly different. Okay. So if you model something as OLS and you model it as MLM, you're going to see that your coefficients differ slightly, right? Okay. And again, we're just still making piles of variance. We're not reducing the overall variance, right? So in OLS, we have a bunch of residual or error variance. We're going to split that up into, in the random intercept model, two piles of variance. So we still have our error, but now we have a random intercept. And then in the random coefficient model, we're going to further split this up into error, our random slope, and our random intercept. Okay. So some of you may have heard of like random effects, between effects, fixed effects, and you're always like, how should I model these? Like, which one should I use? Like, when is one appropriate or not appropriate? What are they? These kinds of questions come about because of a threat to random effects models that's called cluster confounding. So a random effects model assumes that the level 1 covariates are uncorrelated with the random intercept, right? So what this means is that your individual slope is not dependent on your individual intercept, but that's probably not true. This is really problematic because all of our level 1 variables, so all of our alter level variables ego level variables contain information about both alters and groups, right? So in other words, anything happening at level 1, like network size or proportion of gender in the network, takes information from alters, because alters have their own gender, and information from the network as a whole, right? So it could be a function of something about the ego. And then another problem is that when we're pooling these sort of within and between effects, it assumes that within cluster and between cluster effects are equal. So we call that like cluster confounding or smushing, right? And I'll show you an example of what this looks like. So let's return to our example of the effects of instruments on sexual frequency and sexual networks. So in the typical random effects model, we're assuming that the within and between effects are the same by just modeling it with one variable. So the purely between cluster effect would be, do egos with higher mean levels of instrument playing sex partners have higher mean levels of sexual activity, right? So why might that be the case? Put on your sociological imagination. So why would egos with higher mean levels of instrument playing sex partners have more sex on average? Yeah, maybe they're all super attractive, so they're just having sex all the time. Or maybe they're groupies, right? So it could be something about the environment, it could be something about the individuals, we don't know. But that's a different effect from whether egos have more sex with partners in their network that play more instruments versus those that don't, right? And so the bottom one is kind of the one we started with, right? Like people that play instruments are super sexy, so the more instruments you play, maybe I'm more attracted to you and we have more sex, right? So that's a within cluster difference, right? So that's a within effect versus the between effect. And so if we don't do anything to address this cluster confounding, we're assuming that those two effects are equal. And in practice, they're often similar or equal enough, but they can also be very different. So let's show an example of where it might be different. So again, we're still sticking with this ridiculous example. So this is it. Let's say we have three egos here. Jane's observations are in red, Joe's observations are in blue, and Jalissa's observations are in green. If we just ran an OLS regression line, so in other words, we're just completely pooling all of our observations and ignoring clustering, we would have this positive effect that we expected, right? Where the more instruments that people are playing, the more sexual activity they're having in that dyad. So we can do something what's called a between effects regression line, which is where we take each network's average and then we just essentially run a line straight through those averages, right? So this is, if you've ever heard of between effects regression, that's what this is. But if we look at within person differences, this would be a fixed effect, right? So in a fixed effect, you're only interested in within person or within network differences, and you ignore between network differences. So if we modeled our fixed effects regression line, we're not pooling at all, we actually have the opposite effect. So within a person's network, they have less sex on average with alters who play more instruments, right? And so this would be sort of an extreme example. I have no idea why this would be, because I don't agree with that. This is just for the purposes of illustration, you guys. But the point is, we can have these very different within and between effects. And so here's our OLS regression line, right? Completely pooled. Our between effects regression line, which is in practice very similar to OLS. And then we have our fixed effects regression line, which is totally different. Our within effect is very different. So what the random effects model is going to do is produce a weighted average of those two effects. It's going to take some information from the alters and some information from the network as a whole, and it's going to produce this crappy effect that nobody wants to see, a null effect, right? Because it's partially pooled. And so this is an extreme example of where if we ignore this problem of cluster confounding, we can just get the wrong answer, right? So even interpreting this sort of weighted average, right, this random effects estimate here in purple, is really problematic. So what's our comparison group? Is it other alters or is it other ego networks, right? The coefficient is biased, right? Because it's telling us the significance test is going to be biased. It's going to tell us there's no effect here. When there are clearly effects, there are just two different effects. And then we have these meaningful and interesting. I don't know if this is interesting, probably not that interesting. But in practice, you could have interesting effects that are actually masked, right? If you ignore this cluster confounding problem. Fortunately, it's super easy to fix. And there are three solutions. So one is to add a contextual effect. I'll tell you what that is in a minute. The second is to just split the alter level or level 1 variance into within and between effects. You can just explicitly split those up and model them differently and look at the effects of each of them at the same time. Or you could use a fixed effects or a between effects model. So we could just make a modeling decision to not use random effects. We could just use a fixed effects model if we only care about within person differences or within network differences, and we just want to treat between effects as a nuisance. We can do that. Or the opposite with between effects models. One of the first two is probably what you're going to want to do, especially in ego network research, because fixed effects tends to be a little bit less interesting. We're almost always interested in what the ego is doing, what's happening in the network and the network context, right? Okay, so for the contextual effect, you can add a contextual effect of alter or tie level variables by including the aggregated version of the variable. So that's usually just the mean of whatever that variable is at the alter level. If you take the mean of a binary variable, it's just the proportion. That's fine, that's great, we can interpret that. And what this does is it explicitly tests whether the within and between effects are equal. So if the contextual effect is non-significant, you don't have to worry about your estimates being biased due to cluster confounding, because it tells you that those effects are in fact equal or equal enough. But another really cool thing about adding this contextual effect that I think is more interesting than making sure the model is right, is it essentially tests whether the network context matters above and beyond what's happening at the alter level, right? So for example, if we're interested in, let me think if I can think of a more practical example. So let's say we're interested in something like alters political preferences on voting behavior, right? If we take the average, say, percent Democrat or percent Republican in a network and model that, it tells us whether there's sort of an overall cultural effect of political preference in the network that affects our voting behavior above and beyond what each individual alter believes, right? And as network people, and as people who care about egos, that's probably really cool and important, right? Okay, so in the sexual contact example, this is super easy to do. You would essentially just add the mean number of instruments across all alters. So just like you're used to doing when you're creating ego network measures, you just take the mean of that alter level variable, that predictor, and add that to your model when you're modeling the effect of the number of instruments that each alter plays. And so this essentially separates out the effects of ego being attracted to alters who play instruments from having Prince as a sexual partner, right? Because having Prince as a sexual partner, he plays like dozens and dozens of instruments and he's super sexy. That's obviously gonna contribute to your network mean, right? Because if you have Prince in your sexual network, your mean number of instruments is gonna be much higher, right? But then there's also gonna be a lot of variance within those alters. And so by adding that contextual effect, you can explicitly pull that variance out. What we find is that sometimes the ego or the network context can actually affect the true parameter value of that alter level effect. And you don't want that to happen. So another option is decomposing variance. So if you guys have heard of variance decomposition models, or within and between effects being decomposed, that's another option for dealing with cluster confounding. This is almost always what you want to do if you're doing longitudinal modeling where you have observations nested within people, because then you can explicitly model how I'm different from myself over time versus how I differ from someone else on average, right? So it's really great for longitudinal models, but you can use it for network models as well. So at the level 2 ego level, the variable is just equal to the cluster mean. So it's going to be the same as your contextual effect, right? And so that's just the average of all your alters. But then at the alter level, you're going to take the difference between that alter's value and the mean. So essentially that variable becomes the deviation from the cluster mean. That alters a deviation from the cluster mean. So essentially, like, is that alter different from my network on average, right? So do they play more instruments on average than the rest of the people on my network, or less instruments on average, right? And so sometimes this is called group mean centering or cluster mean centering. You may have heard it called that. And so this is another way to do this. So in the sexual contact example at level 2, the variable is just equal to the mean number of instruments played by alters in the network. And then at the level 1, it's each alter's deviation from the network mean number of instruments played, right? And so that becomes an explicit way to model what's the between effect and the within effect. And so if we're thinking across these different kinds of models that you may have heard of, random versus fixed effects, we can think about the difference between random effects and fixed effects models and OLS as varying in kind of the amount of pooling that they're doing, right? And so with fixed effects, there's no pooling, right? You're only looking at the within cluster mean and variation. That's all that matters, what's happening within the cluster. So that's a fixed effects model. This is why when you use fixed effects for longitudinal modeling, it's super conservative, because all you're measuring is change over time. All you care about is change over time. You're ignoring everything else. So that's no pooling. Complete pooling is OLS, where we're just completely ignoring that the clusters or the networks exist at all, and we're assuming they don't matter, right? What random effects is it's somewhere in the middle. So it borrows information from the grand mean or from OLS, but then adjusts it based on what's happening within the clusters, right? So your random effects model, the coefficients can look more like OLS or more like a fixed effects model, depending on essentially how much clustering there is in your model. So as your interclass correlation, which remember is a measure of how similar alters are within networks, as that goes to 0, random effects looks more like OLS. The coefficients will be more similar to OLS. If it goes more towards 1, your coefficients start to look more like fixed effects. So in ego networks, in principle, what happens is that you typically end up like somewhere around here, right? So typically, you have a lot more within variation than between variation, right? And so you end up having alters that are somewhat similar to each other, but like not wildly different, right? Because we're all just like living in the same social world or relatively similar social world, right? And so usually you're going to use a random effects model rather than a fixed effects model. Okay, so what does the output or the interpretation look like? Hopefully you're not scared. Hopefully you understand this conceptually, because the output is even less scary, because it's basically almost exactly what you're used to, and then some extra things that we can look at if we want to. So you can do this. It's not scary. Okay, we're going to look at Stata. I still use Stata, you guys. I'm over 40. So I don't use R or Python. I prefer the SUV. I'm gay, so mine would be a Subaru. But basically, I don't even touch R. It scares the shit out of me.
I think that rolls as a compliment.
Yeah. No, you don't. That's funny. Anyway, so I'm going to show you output in Stata, but like in practice, all these different programs are going to spit out something really similar looking. It's going to have the same components. But if you're not used to Stata, then, sorry, that's what you're going to get. So let's say we want to look at like a more real example, right? Like something that we might actually want to study. So we may want to look at the effects of ego and alter gender on the number of support functions provided by an alter to egos, right? So support is super good for you, right? It's good for health. It's good for social mobility. It's good for lots of stuff. So we might want to predict whether alters are providing more or less support, what characteristics of alters affect that, what characteristics of networks as a whole affect that, et cetera. So we can model this with multi-level modeling. And again, in this case, we have our outcome, our intercept, and then we have alter gender. And each alter is going to get their own gender. And then we have ego's gender, right, in this model. And then we have our random intercept zeta and our error term, because we've split that variance. So we can run this in Stata, and the first step is always to run what's called an empty model, which just means a model without any predictors, without any covariates. And this allows us to first assess the random parts of the model, or the variance in the model, before we've started putting in predictors that explain that variance, right? And so we might just want to know, like sort of off the bat, what does our model look like? So here, we have psi, which is this here, and it's essentially just the between level 2 egos variation. So this tells us like how much variation is there between egos. And then we have theta, which is variation within egos. So what we can already see is that there's way more variation within egos than there is between egos. And so this is going to tell us that our model is going to look more like OLS, right? But we can actually explicitly test whether we even need an MLM, right? So given this level of variation within and between, I might look at this and be like, it's marginal whether I even need a multi-level model. I might just be able to use OLS. But Stata, as beautiful as it is, just explicitly tests this for us when we run this empty model. And so this is an LR test here at the bottom. So if it's significant, it basically tests whether the between and within effects are equal. And if it's significant, you need multi-level modeling. So even though we have more variation within here and our model is going to look more like OLS, we still have to pay attention to clustering. I can run my interclass correlation, which remember is almost just like an R value or a correlation of alters within ego networks. And so it's about 0.06, so modest correlation, but still significant correlation, right? This doesn't contain 0. So again, this is just more evidence that we do need to use a multi-level model, but our coefficients probably aren't going to be wildly different from what we would find with OLS. But you still have to please those reviewers. And so then I can run the model with predictors. So here I'm predicting number of support functions. I have ego gender and alter gender here modeled as a binary variable where 1 is women. And so this is the part of the model up here that we care about, right? This is the model that part of the model that most people ignore. This is the model for the variances, which we just talked about. So we have some assumptions about this, which I won't go into today because I don't have time. You can test those assumptions, and then if you want to, you can just ignore this, right? Or you can talk about it and interpret it if you want to. But this is the stuff that we really care about. So this is the fixed part of the model. It's the model for the means, and it's just business as usual. You're going to interpret these variables exactly as you would in a regular OLS regression model. So see, MLM is not scary. You guys can do this. So here if we want to look at what these effects are, we can see that ego gender, the effects of ego gender on how much support an alter is providing is not significant. Doesn't matter. But we can see that alter gender does matter, right? So females or women provide more it's Trump administration, so females provide more support functions on average than men do within ego networks. And then I have to add my contextual effect, right? I have to do my due diligence because I don't want cluster confounding. I don't want to assume that the within and between effects are the same. And so here what I'm going to do is just essentially model the proportion of women in the network, right? And so I add this value in. It is a significant parameter, and you can see that the effective alter gender changed a little bit, right? So it went from 0.07 to 0.08, right? So it did change that parameter a little bit. And then what this effect tells us is that networks with more women in them on average are actually less supportive on average, right? But within the network, we tend to rely on more support, get more support from women relative to men in our network, right? So there's kind of a feminizing effect of the network. And so maybe we could interpret this as when you have a network with a lot of women in it, everybody else is doing less. Maybe they're coordinating. They're all sharing the burden or whatever of support. So there's a lot of things we might hypothesize. But this is a situation where it's interesting because the within and between effects are opposite. So I could decompose variance here if I wanted to, but I'm not going to do that in the case of this predictor because it's binary. So, and thinking about like what the deviation is from the proportion in the network, like gender can't deviate from average gender, right? That interpretation doesn't make sense for binary variables. So if you're using binary variables, you're interested in those, just use the contextual effect. You only want to split up the variance if it's a continuous or maybe even like an ordinal variable. Okay. Do you guys do you feel like you can just go do this now? You're like, hell yeah, I've got this, Brea? Yes? No, you don't look that confident. Any questions before I move to dynamics? Yeah.
So just thinking about adding in contextual effects, is this something you always have to do, or do you test for clustering confounding as part of your best
That's how you do test for it as best practice, and that's how you test it, is you add it in.
Oh, okay.
And if it's non-significant, you can drop it.
Okay.
Yep. But you might want to say, like, there is no network effect here, above and beyond what's happening at the altar level, right? There's no network effect above and beyond the altar level effect, which is interesting often, right? And usually there is a network level effect, honestly. It just doesn't always change the effect of the altar level variable much, right? Just like in this case. Yeah.
Would you be able to share code with us to see what's kind of happening behind the scenes?
Yeah, well, so yes, so I have a whole bunch of like exercises and code. It's all in Stata. Although Gabe, didn't you do it in R? I made Gabe translate for me.
I can share our versions as well.
Hell yes. Okay. Does anyone actually want Stata? Okay, like Tom Valente wants Stata. I love you so much. Yeah, like 2 people and they're all over 50. Okay, so I can share the Stata versions and then Gabe can share the R versions because we did at some point, yeah, do this. Yeah, it's so long ago. Yeah.
I was wondering, how do you usually identify what counts as a test? Is it driven by your assumption?
So that's a really great question. So I think it could and should be motivated both by theory and by getting the right parameter estimates, right? So anytime you're modeling something with a random effects model at level 1, you want to test your contextual effect just as a part of due diligence. And that's just making sure that your parameter estimates are accurate, right? But often, always really, as a network person, I care about the network level effect, right? Whether there's an effect of the network context, the network culture, above and beyond the alter level. So I would say it's both, right? So you have to do it because you just have to do it, but then it's usually interesting and interpretable. So.
If you have multiple independent variables and you're at this step, does it make more sense to test them independently, or do you put them all in model at once with the contextual?
Yeah, that's a great question. It really depends on how correlated those independent variables are. So, I mean, as you know, with network stuff, you often have a lot of multicollinearity issues. So I would just test that and see how correlated they are. If they're modestly or even moderately correlated, you're usually fine to put them all in the model at the same time. Other questions? All right. Cool. You guys got this. See, it's not that awful, right? It's not that scary. It seems scary, but it's super not scary. Okay, so ego network dynamics. So I have 20 minutes. I think I'm actually like doing pretty well. Okay, so I'm gonna do a little bit of like what do we know about dynamics, and then I'll talk a little bit about how to model them. And so I don't model them in like the fancy ways. I model them using like tools that everybody uses. And I would say that it's for some like philosophical reason, but it's just because I'm old and I don't want to learn new things. So I know there are like ergms for ego networks, you know, like the probability of a tie, you know, forming between like an ego and an alter. Yeah, I don't do any of that. So, you know, there are other people here who could probably teach you to do that, but I'm kind of old school. So you're going to get the old school version. But okay, so social network dynamics, what do we know about them? So a lot of research only provides kind of like a snapshot of networks at one point in time. But this is really problematic because we know that networks are super dynamic. They're always changing, especially at the level of alters, like who the specific people are that make up the networks. Those change a lot and they change pretty quickly depending on what's going on in your life, social context, things that are happening internal to the network, et cetera. So the key is to sort of disentangle what's real change from what's methodological artifact. And so we know that structural properties of networks tend to remain pretty stable over time. So Ben Cornwell, for example, has published a couple of really great papers using NSHAP data on what he calls homeostasis in networks. There's been really interesting research on social signatures, a lot of which comes out of like anthropology. And so there's this idea, like if you've heard of Dunbar's number, that like we could only maintain a certain number of relationships with our like feeble human brains, and that this drove evolution. I actually love that shit. But essentially the social signatures literature sort of came out of that, and it's the idea that we as individuals have these kind of like set points in terms of how we tend to interact, how many friends we keep, if we tend to introduce our friends to each other, how much we rely on them for support, et cetera. And all these things drive sort of structural or aggregate properties of networks. And so even though like the people that might, that make up our networks might change a lot over time and be super dynamic, we kind of have these social signatures that represent how we interact or tend to interact on aggregate. And so this is all just a reflection of this idea that these structural or aggregate properties tend to stay pretty stable over time. But there's tons of turnover or churn in the individuals that make up your network. But what this means is that you may constantly be losing ties, but that doesn't mean that it's a bad thing. It's not necessarily pathological. So, you know, I published a couple of articles about like people with mental illness and their networks, and any network loss was always pathologized. But often people were just replacing people in their network because those people sucked or like didn't provide the kind of support they needed, right? So we tend to pathologize network loss, but it could just be sort of a healthy turnover or sort of a replacement. And so we want to be able to distinguish those things, right? When we're studying networks. So in terms of like how many ties persist, there's a lot of research on this. You know, Barry Wellman did this, has the East York study, and so he found that only 27% of ties persisted over a decade. Suter and Keaton did this study of caregiver support networks, and 30% of ties persisted over a decade. And then David Morgan did this research on recent widows. Only 22% of ties persisted over 1 year. Again, that's a period, a tumultuous period in your life. So again, like we might expect that there are these external forces that affect the amount of dynamics. And then this figure is from Cornwell, and it's kind of complicated, but essentially it measures the amount of turnover. And these are wave one network losses and wave one network additions. And you can see that there are some losses and additions in the overall number, but the sort of like common feature here is that networks are staying the same size, but there's just like a ton of turnover in those networks, right? And so if we're thinking about what drives membership turnover in networks, there are at least 3 things. There are probably a lot more, but these are the 3 things we tend to study. And so one, and this is really important in terms of how we model networks and why we care about dynamics, is selective activation of latent ties, right? So we all have these like larger peripheral networks. We have a lot of people that we could name, that we could rely on, that we could get something from, that we could reach out to, but we don't do that regularly, or we don't think of them in response to whatever our name generator is. Because when we're answering name generators, we're thinking about our like typical status quo, right? Or who we interact with most regularly. And so we have all these latent ties that are sort of selectively activated, right? To be active for whatever we need them for. And so any given sort of slice, cross-sectional slice of a network is often gonna miss a lot of these latent ties or peripheral ties, which can nonetheless be super important for all the outcomes that we care about as network researchers. And so, you know, sort of paying attention to this is really important. But beyond that, we could also have sort of real internal dynamics, right? So there could be things that happen in our network, like we could have a lot of conflict in our network that affects turnover. We could have burden, caregiver burden, right? Like lots of other things that are happening sort of internal to the network that drives membership turnover, that drives people out of the network and seeking to bring new people into the network. But then we also have external dynamics, right? So when we have sort of a shakeup to our network, like, you know, most of you probably went to graduate school at some point. For some of us, it's been a while. But you remember how much of that shook up your network, right? You had all of a sudden, like, you were introduced to all these people that, you know, it's like boot camp. You're all like surviving this thing together. You're all stuck together. And that really changes your network. It probably changed how much you communicated with your family, how much you communicated with your friends at home, et cetera, right? And so there are these sort of things external to the networks. One of my favorite books is Kai Erickson's Everything in Its Path, which is about, it's this great ethnography, network ethnography, which is essentially about how this Buffalo Creek disaster in Appalachia just completely upended networks because everybody had to move and they just displaced them randomly. And so it's about how much it changed networks and how that affected people's experience of coping with this natural disaster. So I highly recommend, but that's just another example. And obviously, as climate change worsens, we're going to have more and more of these kind of displacements. And more recently, people have studied this with respect to things like Hurricane Katrina. And so I love this quote by Barry Wellman. I'm like a huge Barry Wellman fan. Some might call me a stan. But basically, he has this quote where he talks about how personal network dynamics operate similarly to biological evolution, which is to say that they undergo these kind of gradual, random ebbs and flows across the life course, but then they're punctuated by these intense, rapid shifts that correspond to significant events or significant changes in your life. So things like getting a divorce, having a major acute illness, which is something I've studied a lot, natural disaster, which I mentioned, migrating, or even just moving across the country, retirement, parenthood. If any of you guys have kids, you know how much your networks changed when you had kids, right? And so we have these kind of gradual, random ebbs and flows where people are coming and going slowly, and then we have these big shakeups. And I really like that way of thinking about network dynamics. Another really important thing about network dynamics is how networks tend to be structured, right? So ego networks tend to have these two basic components. So they tend to have this smaller and more stable core network. It's usually very densely connected. It's often mostly comprised of kin, and it tends to be highly supportive. And those are very stable, right? So this is the small part of the network, core network, that tends to remain stable over time. But then we have this much larger set of temporary or latent or sporadic ties that are in what I would call the periphery. And so what we find is that you see a lot of triads between members of the core and the most adjacent peripheral members. But then we also have a lot of pendants, right, where you just have these like peripheral members hanging out there. But at any given time, you could activate one of those peripheral members to come into your core. So let's say that ego, for example, develops cancer, and they have a latent network member who's had cancer before. And so at that point, experiential homophily becomes really important. And so they might activate that person into their core, and it might become one of their regular supporters, right? So this is kind of how network dynamics work. And what we find is that most of the turnover occurs in the periphery, right? That's where most of this churn happens. But this periphery turns out to be a big problem for cross-sectional network studies, right? Because people engage in these sort of brief, meaningful or sporadic periods of contact, right? So like, I tend to be somebody who, like, I have a lot of friends that, like, when I see them again, it's like we never, no time has passed, right? So if you were to happen to do a network survey of me, right after one of my good friends that I hadn't seen in a year visited, I might name them as a core supporter, right? Whereas I wouldn't have if you had happened to interview me a month previous. So that can cause like more peripheral members to be pulled temporarily into the core. And so the sort of likelihood of these sometimes there, sometimes not relationships being present is essentially kind of random, right? But you're counting it as real change when you're thinking about network dynamics. And so the flip side of that is that when peripheral ties are not captured, they're assumed to be absent, right, rather than inactive. And so Mario Small has done a lot of really great work on these incidental ties, right, or people whom we don't talk to very often. Maybe we only talk to them once, but nonetheless, we talk to them about really important things, and they could have really consequential effects on our future behavior, for example. But the point is kind of the instability in what you're seeing in these ego networks doesn't necessarily mean real change, but it might, right? Okay, and so the first problem with how to capture these dynamic properties is understanding whether you're seeing real change or whether it's a methodological artifact. So about 5 to 10% of the time we find, and this is across a couple of studies, that respondents forget to name alters from a previous wave. They just forget them, right? They didn't mean to leave them off. There's nothing different. It's just like human error, right? Another important problem is panel conditioning. So what we find in almost every longitudinal network study I've ever done is that the number of alters named wave on wave gets smaller and smaller and smaller and smaller, right? And you might wonder, why is that, right? We might say like, oh gosh, like, community lost, like, God, people just don't have, as big a core networks as they used to, like, blah, blah, blah. But some of this is about panel conditioning, right? So if you're measuring the same person over and over and over again, they learn pretty quickly that the more alters they name, the more work they have to do in that survey. But they're getting paid the same, right? And so this can create panel conditioning. And then you also have just basic error, like respondents giving different names, nicknames, spellings, and subsequent waves. And so it's just like basic error that is undetectable unless you're sort of looking for it in the way that you're measuring network dynamics. The second problem is determining what kind of alter level changes underlie network level change, right? So the best way to think about this is through an example. So let's say that I look at a network level, like aggregated measure of something like mean frequency of contact. And I find that mean frequency of contact has changed, right? Is significantly different between waves 1 and waves 2. This can be due to 3 different kinds of change, right? All of which can potentially signify really different things about me, my life, my outcomes, etc. Right? So first, it could be that I have decreasing contact with alters who are present at both waves. So I have the same people in my network, I'm just seeing them less, right? So maybe I'm working more, maybe I had kids, like who knows, right? Another possibility is that I'm losing alters with whom I used to have particularly high contact. That could be devastating, right? Unless that person is like a toxic person, right? Or it could be that I've added new alters with whom I have infrequent contact, which could be good, right? It could mean that like I've made a new group of friends and we don't see each other a lot yet because we're just forming our friendship, but that could be a really positive thing. So disentangling all these different types of underlying dynamics are super important, and we don't see that when we just look at aggregate network characteristics across time, right? So there's a sort of easy solution to this, is it real change or is it methodological artifact problem? And that is that in each wave of follow-up study, I would strongly suggest that you do this. Have egos name their current alters, right? So just as you collected it in the first wave, don't change anything. So maybe you're saying, who do you talk to about important matters? Ask it the exact same way in the second wave. And then subsequently, you show them their roster from the previous wave. And then you have them, first of all, match alters across waves. So this gets rid of this problem of providing a nickname, right, or misspellings. And then ask them why they didn't name any alters that were dropped, right? So why didn't you name this person? And then if they say they forgot them, you add them back in, right? And then you proceed with your name interpreters. And then actually, you can use that, why didn't you name this person? It provides super interesting data. So like we've published papers just on why people drop out of the network, because sometimes you get these really rich answers. Often it's like they died, right, or something. But often it's really interesting. And so understanding like what the variation is and why people are dropping alters, and then you can predict that with ego characteristics, things happening in ego's life, and then that itself becomes a meaningful and interesting research question. And so it might look something like this, right? So this is your wave 1 roster, this is your wave 2 roster. Another great thing about saying, like, why didn't you name this person, is like what we find, what our interviewers report is like, let's say I say, why didn't you name Brian? People have a hard time lying to you, and they'll just say they forgot them, right? So when you have to make up a reason why you didn't name your kid in the second wave, usually you'll just add them back in, right? You're not going to be like, well, my kid sucks, you know? And so this really helps with panel conditioning as well, right? When they actually have to report something of substance about why they were dropped. Okay, so that takes care of the sort of methodological part of it. Then in terms of how we want to measure network change or think about model network change over time. So one thing we can do is just have these aggregate network level measures that capture network turnover. And so typically in these cases, we're pooling 2 or more waves. So you'll have kind of like a moving, like pooled situation. This probably has a fancy name if you're a computational social scientist. But basically you just take waves 1 and 2 and you say, what are the number or proportion of alters dropped, added, or stable across 1 and 2, 2 and 3, 3 and 4. So you end up with 1 less observation than actual time points that you have, right, in the end of things when you have your data set. And so this is one way to do it. We also created this measure of network turnover, where you're essentially pooling across 2 waves, right? So I have wave 1 and wave 2. This is pooled, where I'm just adding them all and assuming they're like, I don't know, maybe part of my larger network. And then I take the number dropped or added, so anyone that sort of changed, and then divide that by the number of unique alters that were pooled. And so like in this case, you can see that you have 3 stable alters across these 2 waves, and then 3 alters that were new or dropped in each wave. And that gives us a turnover rate of about 67%, right? So that's an easy way. If you don't want to think about added versus dropped, you just want to think about sort of the overall level of churn. If your goal is to describe network level change, you can just very simply compare ego network characteristics over time. So what's my average network size at wave 1 compared to wave 2? What's my average frequency of contact at wave 1 versus wave 2? I can also measure the difference between 2 waves, so like the average growth in networks or the average decline in networks. And so this is from Cornwell's. I should update this because he just did a new one in 2021. But this is basically what he's doing here. He's comparing mean characteristics of networks across waves. So you have, like this is wave 1 network size, wave 2 network size, the difference between the two, and then the percent of networks that decrease in size stay the same size or increase. And so this just gives you sort of an overall snapshot of how networks are changing. If the goal is to describe alter level change, which again, I think is really important, right? Because these network level changes mask a lot of important stuff. I want to distinguish the alters dropped, maintained, or added across waves. And I can just present the number or the percentage of each, right? So how many alters were dropped, how many were stable, how many were added. I can compare the characteristics of each, right? So I might want to say something like 75% of stable alters are very close compared to 35% of those that left the network. That makes sense, right? We tend to retain people that are closer to us, that are more supportive, et cetera. And so this is what he did here. He compared characteristics of stable, lost, and new alters. So this top one, for example, is the kin relationship. So among those that are stable, again, these are the same people, which is why they're very similar, but they're 78% kin, but only 48% of those that were dropped and 47% of those that came into the network were kin, right? So what this tells us is that overall, we tend to retain kin more so. The kinship ties tend to be more stable than other kinds of ties, right? And so you can do this for any network characteristic. If your goal is to predict network level change, you're going to use 2-level longitudinal multi-level models or growth curve models, which is exactly what I just taught you. So you guys can totally do this now, where the observations over time at the network level are nested in egos. So now you have observations at level 1 instead of alters, and you're aggregating to the network level. So you could model, for example, how network size changes over time, and those observations are going to be nested in egos. So typically when you're doing these kind of models, you're going to model the effect of time and often time squared, because usually things don't change linearly. And those become kind of your key predictors. So how does network size change, for example, with age, right? So you guys have probably heard of socio-emotional selectivity theory. It's this theory that like the closer you get, it's very morbid, the closer you get to death, the more you want to invest in ties that are closer and more supportive, and so you shed a lot of your peripheral network. We find mixed support for it, actually. But basically, so what that theory would predict is that as people age, their networks get smaller and more supportive, so we could actually model that with a multi-level model. And so in this case, you almost always want to decompose that variance into within and between effects, because the between effect is a purely growth or change estimate. Right? It just tells me how I'm different, how my network is different from myself at prior time points. And then the really cool thing you can do with these growth curve models is interact time with other predictors to test whether networks change at different rates as a function of other variables. So for example, I might hypothesize that the rate of change in networks over time as you age varies by gender, right? So we might expect men's networks to contract over time with age, and women's might not, which is what we find actually typically. And that's just with an interaction term between time and ego gender. If your goal is to predict alter level change, you can use 3-level, longitudinal, multi-level, or growth curve models, right? Where observations over time are nested in alters, which are nested in egos. And it's going to be the same in that you're going to measure the effective time in time squared. So I might, for example, want to measure whether an alter drops out of the network between 2 waves. And so I could say, for example, how does time in the illness career affect whether an alter drops out of the network? And then similarly, I can interact time with other predictors. So does the likelihood of an alter dropping ego as they move through the illness career vary as a function of how that alter is related to ego? So we find, for example, that kin tend to stick around and support and be caregivers, whereas non-kin might be more likely to drop out of the network as you move through the illness career. And you decompose the variance the same way, except you have 3 levels. So you have your overall mean, and then the second level is deviation from the higher order mean, and then the third one is deviation from the second order mean. But otherwise, it's done the same way, and there's lots of good resources. I would suggest Lisa Hoffman's book on multi-level modeling and growth curve modeling. It's LESA HOFFMAN. She has like the clearest, most amazing like explanation of this ever. I think she uses SAS though, so don't judge her. You'll have to, whatever, Jim. So you'll have to find your own statistical modeling, but there's a lot of resources out here. Brandon Bartels also is another one. I really like his resources on multi-level modeling if you want more follow-up stuff. I think he's a political scientist. So anyway, yeah, so you can use those same kinds of models to model network change, and it's just perfect. It's ideal for that. So, and now you know how to do it. So that's it. Dude, look at that. 10:34. Oh my God. I'm so good. Yes. I don't know, do we have time for questions?
Time for questions. I'll come up and switch out the mic and stuff.
Okay.
But,
All right.
I mean, they're just going to listen to me ramble on for now to lunch. So yeah.
Cool. Yeah, sounds fun. Yeah.
Peripheral ties, you talked about the importance of those, and also really small, and a lot of this work about like the avoidance of poor ties, but looking at the implications, they can be incredibly valuable in points of vulnerability, social and structural vulnerability, and so what I'm finding is that participants are really biased by the important matters to
Yeah.
mention those, but like in cognitive testing, they're like, I actually don't really talk to my mom about these things because she doesn't believe in mental health things as well, culturally. Yeah, or a boyfriend, or like a lot of those things, and I am interested in measuring and using weaker ties, peripheral ties as intervention points, so some really great innovations and ideas at those, but they're highly volatile. Two time points I have career level, so I don't have anything like longer than that.
Yeah.
But how do you develop name generators that can look at both of those
Yeah.
dynamics that aren't incredibly burdensome? Because just purely doing cognitive testing by pilot testing is exhausting to me and my research team, and I'm trying to figure out how to capture both of those things because they are essential.
Yeah. So I think I have a few ideas. So one way is that, I mean, I always use the important matters name generator just because it's so comparable. Like, you have the GSS to compare to, lots of studies use it, or some version of it. But then I ask, I've done a lot of work on discussion networks, and I'm also super interested in discussion networks, right? But you want to ask about the specific kind of discussion that you care about. So like we have a set of name generators that ask specifically about health, who you talk to about health matters. And then we even further break that down into who do you rely on to talk to, who talks to you whether you want them to or not, and who is a burden to you in talking about their health, right? So you can get at sort of these different kinds of health communication that you don't get if you just ask, first of all about important matters, or even if you just ask about health matters writ large without asking about sort of the functions of those communication. You can also explicitly ask, who do you avoid talking to about health? And then get information about that. And then in terms of gaining access to those more peripheral ties, I think you could do what Mario did, which is think about the last time you talked about this. Who did you talk to? And you can also just explicitly ask about weak ties. This is the beautiful thing about name generators. You can do whatever the fuck you want. Like you can literally do whatever you want. So people will ask about like, what's the standard name generator? And I'm like, what do you want to know? Like it totally depends on your research question and your theory. So you could say, like, is there a time when you've talked to someone that you're not close to about health? Who is that? Tell me about their characteristics. Or, tell me about a couple of instances, right? So again, it's just like the really key thing in terms of developing name generators is to think about, like, what are the mechanisms that I think are driving this thing that I care about? And then how do I get at those mechanisms? And then don't be constrained by what other people have done. But I would like ask other people, right? Don't just like make things up. Like ask other people if this makes sense. Like whatever, your collaborators or your mentors or whatever. Yeah.
So love that you do all this differentiating your generators, but is there an optimal number that you probably should not exceed in your survey?
Yeah, that's a great question. I really like to push the bounds of that. And so like I think in our longitudinal study of older adults, I think we have like 10 or 12 name generators. And so we really try to round out the peripheral network. So we ask about like neighbors that you talk to regularly, any kin that you talk to regularly, coworkers or volunteers that you talk to regularly. So we're still getting sort of regular interaction partners, but we're not limiting it to a specific function. But then the way that we deal with that, because then you have a really long interview, is we randomize alter-alter ties, which I think I talked about last time or maybe the time before. I don't know, these are all blurring together. And one of my collaborators wrote a paper about how to do this and basically validating it. So you can just like randomly select alters for alter-alter ties. And as long as you randomly select your average number of alters across your sample, then you're like good. Everything is like within like 95 to 98% the same. It's fabulous. And that's really where if you start to get a ton of alters, that's where like the majority of your time is spent, because there's that exponential relationship between number of alters and alter-alter ties. And you can also randomize for name interpreters if you want to. Randomizing works super well, turns out.
Yeah, would you recommend you randomize per generator?
That's a great question. No, we typically randomize just overall. And there's a lot of overlap between generators too, right, also often, right? So a lot of those are, would be named in response to multiple generators also, especially when you're asking about a lot of functions or something. Did you, Gabe?
I mean, in regards to this and the sort of key, I would also plug newer tools like Network Canvas,
Oh, Network Canvas is amazing.
which allow you to draw very easily between nodes. They can construct their network and very easily quickly draw it into users.
Yes, yeah, so Network Canvas is amazing. I use it in all my studies. I cannot speak like highly enough. And now they have a web version, so you don't have to download it. It's still in beta, I think, but I have grad students that are using it, so it's very close. And it is amazing. So the things that make it faster are that you do binning. So like all your ties are over here, and then you have like bins for your name interpreters, like, like strongly, somewhat, not at all, and you just like literally take your finger and just like bin them like this, just move them over. It's super, super fast. The alter-alter ties they can get a little tricky if you have large networks, because like you miss ties. So I always still tend to do those alter by alter and just randomize, but we actually built the randomization function into Network Canvas. And it's awesome. Like I cannot speak highly enough. Yeah.
I was wondering, how do you want to change in the sense that someone who drops out of, for example, in the discussion network that enters into a different, and is added to a different nation?
Yeah, so you can just model that essentially as a dependent variable, right? So did someone move out of the important matters, for example, and into something else?
So, did it consider as a binary in terms of?
Yes, yeah. I mean, you could probably do more complicated things like, I don't know, following their trajectory or something, if you wanted to. But yeah, I mean, anytime, any interpreter or any generator you can use as an interpreter, right? You can just use that as a characteristic of the alter. Like, what they were named in response to just becomes a variable. Yeah.
Like I'm forgetting all like that concept, like that you
other place that they can.
Structural equivalence?
Yeah, structural equivalence, yes. So if an ego is structurally equivalent to another, you have like multiple equivalents of structurally equivalent egos that have been like have been in the country like ego that they are immigrants, have been in the country like different times like have been in the country for 20 years or 5 years, and those networks are different. Could you treat that as different time frames and
Do you mean like model the effects of like how long someone has been in the country on, yeah, you can do that. You can do anything you want. Yes, that makes total
That's
sense.
a classic pseudo-panel design.
Yeah, yes, exactly.
The only thing is that you have to just know theoretically that you have events that happen in real time that you are essentially averaging over or treating as something.
Yes, and the other thing I would say is be careful if you just have like a bunch of people interviewed at one point in time that have been in the country for different lengths of time. Don't impute like change, because you're not really measuring change. You're comparing characteristics of someone that's been in the country a shorter versus a longer time. You can't say that like acculturation causes networks to become blah, 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 right? Because you're not actually measuring change over time. Or maybe you are, I'm just saying. Yeah. Yeah, and we can talk, I mean, I'll be around for a couple days. I'm sorry, is this okay?
Yeah, let's do take 2 more questions, and then we'll take a break, get some coffee, let people stretch their legs, go to the bathroom, and then we'll come back.
Yeah, and I'm also around, so feel free to grab. Okay, so I think I saw yours up.
Can you combine MLM with network correlation model to, because I'm wondering how do you account for the correlations between cultures in MLM?
So that's exactly what MLM does. So correlation between alters is just dependency or clustering. So that's literally exactly what this whole thing does, is accounts for that.
Correlation between alters within ego?
Yes. Yeah. If you're confused, I really messed this up. Yeah, I mean, it's like, you know, alters are more similar to each other because there may be some kind of network effect or network culture, right? So your network might provide more support than I provide on average because that's the culture of your network, right? Like you guys do stuff for each other. My network's a bunch of jerks, right? MLM captures those mean differences and explicitly models them as clustering. Like that's exactly what this is doing. We can talk after if you're still, yeah, okay. Yeah.
I love the connection you made between biological networks and personal networks, and I was wondering if you had any specific insights for organizational networks. For example, you know, when we're talking through some of the differences from like the way I've seen in organizational studies, you know, there's like an excitement factor. In the first wave, oh my gosh, partnership is great, I work with so many people, and then the next phase they're like, I don't work with anybody, I'm tired of this, not getting me fill out the surveys.
Yeah.
But other examples and things like that that we're really aware of from doing organizational economics.
Yeah, so I think that's a great point, is that you can have panel conditioning for lots of reasons. It's not just because people don't want to, you know, answer all your questions. So I think the key thing for that would be trying to assess whether that's real differences in how much people are working together or just a fatigue in like talking about the rah-rah, because those are two very different things, right? So asking some follow-up questions about that. So I think asking why you don't work with this person anymore, I think even in the case of what you're saying about saying might cause them to say like, actually I do work with them, but you know, I'm just not that excited about it anymore or whatever, right? So yeah, and just asking the follow-up questions, doing a little bit of cognitive interviewing is always helpful in terms of assessing the degree to which that's a problem.
And when you say follow-up questions, because I mean that you're working on, is that embedded into your instrument where like if there's a drop-off, they can automatic drop?
Yep.
It's not like a discussion, it's a written response.
Yeah, it's a survey question. And then we have like set responses that we see most often, and then there's an other, you know, that you fill in the reason. And that's often where you get the most interesting responses. Sometimes colorful responses.
All right, Bree will be around all week.
Thank you.